Another way of solving a system of linear equation using the LU factorization or the LU decomposition is by the Crout's method. The Crout's method is actually similar to that of the Doolittle's method. However, in the Doolittle's method, the diagonal elements of the lower triangular matrix are equal to 1. Wherein here, the diagonal elements of the upper triangular matrix are equal to 1. So, basically, we're going to use the same expression, matrix A times X equals B. So, we're going to decompose matrix A to its lower triangular and upper triangular matrix. And if we're going to substitute this one in here, we have LU multiplied by X equals B. Now, if we're going to let UX be equal to Y, therefore we have Ly be equal to B. So, if we're going to solve for the value of X here using the LU decomposition, we need to solve for L and U first, and then we're going to uh, multiply L, or the lower triangular matrix, by an unknown vector, so we're going to call it y vector, and we're going to equate it by the constant matrix. And then solving for the value of y, whatever the value of y is, we're going to use that vector to solve for the value of x. So in order for us to illustrate this, so let me just illustrate this one using our example here below. So again, we have a system of four equations with four unknowns. So we have x1, x2, x3, and x4 as unknowns. So the first thing that we are going to do here is to create a coefficient matrix. And the coefficient matrix would be 1, 2, 1, 1, negative 1, negative 1, 1, 1, 1, 3, 2, 1, and we have negative 1, 1, 2, and 1. So this would be our coefficient matrix. And this would now be multiplied by the unknown vector. We have x1, x2, x3, and x4. And this would be equated to 1, 2, 3, 3. Using the Crout's method, we are going to decompose the coefficient matrix into its lower and upper triangular matrix, wherein the diagonal elements of the upper triangular matrix are equal to 1. So if you're just going to rewrite here our coefficient matrix, so we have 1, 2, 1, 1, negative 1, negative 1, 1, 1, 1, 3, 2, 1, and then we have negative 1, 1, 2, 1. This would now be equal to, the lower triangular matrix would be A, B, C, D, E, F, G, H, I, J. And then its upper diagonal would be equal to 0, 0, 0, 0, 0, and then 0. And for the upper triangular matrix, again, the diagonals here would be equal to 1. So we have 1, 1, 1, 1. Then this would now be K, L, M, N, O, P. So 0, 0, 0, 0, 0, 0. There we go. Now, we are going to multiply L and U, and then we're going to equate each corresponding element to the given coefficient matrix. Therefore, in that way, we can now solve for the values of A until P. So to do that, let me just multiply this one with this. So we now have, this would now be equal to first element. So the first element, the first row, multiplied by the first column of the second matrix. So we have A. This would be equal to A. And then for the second column, or for the second element here, we multiply this one with this. Right? So that would be A multiplied by k, so that's a multiplied by k, and then 0 multiplied by 1, 0 multiplied by 0, 0, and so on. And for the third element in the first row of the resultant matrix, we multiply this one with this. Alright, so that would be a multiplied by l, a multiplied by l, and then 0 multiplied by n, 0 multiplied by 1, 0 multiplied by 0. And finally, for the first row of the resultant matrix, we're going to multiply the first row with the last column. So basically, that would be equal to a multiplied by m, because 0 times 0, or o, I should say, and then 0 times p, and then 0 times 1. So that is the first row. For the second row of the resultant matrix, we're going to multiply the second row of the first matrix with each column. So for this particular element, we're going to multiply this row with the first column, and that would be equal to b plus, alright, so that's b times 1, c times 0, so that's equal to b. So b times 1, that's b, c times 0, 0 times 0, and 0 times 0. So that's basically equal to b. And for the element here, we're going to multiply the second row by the second column. So that would be b times k plus c. b times k plus c plus 0 plus 0. For the third element on the second row here, we multiply this one with the third column here. So b times l, that's b times l, c times n, so plus c times n, and then 0 times 1, 0 times 0. So let me just arrange this one. I'm just going to move it a little bit here, and then also this one. We just move it a little bit here, and move it a little bit here, so that we will not be confused later on. Right? Alright, there we go. And for the last element of the second row of the resultant matrix, we now have, or we multiply the second row with the last column. So that would now be b times m plus c times o plus 0. Alright, so plus 0 times p plus 0 times 1. That would now be our second row. For the third row, right? So for the third row, we repeat the process. So d times 1, 0 plus e times 0 plus f times 0 plus 0 times 0. So that's basically equal to d. d times k, so that's dk, plus e times 1, so that's equal to e. f times 0, 0 times 0. Third row, we have d, or third row, third column, we have d times l, so that's d times l, e times n, f times 1, so that's plus f. And for the last element of the third row, we have d times m, plus e times o plus f times p, plus 0 times 1, or basically equal to 0. And for the last row, we now have g times 1, so that's basically equal to g. Because h times 0, I times 0, j times 0 are equal to 0. For the second element here, we have g times k, so that's g times k plus h times 1, so that's plus h. And then we have I times 0 plus j times 0, so that's basically equal to 0. Third element of the last row. So we have g times l plus h times n, so that's h times n, I times 1, so that's plus I, and then j times 0. And for the last element here, we have g times m, so that's g times m plus h times o, so that's h times o, I times p, so that's I times p, and lastly we have j times 1. So plus j. So let me just delete this one. So plus j. Alright. Now, we already multiplied the lower triangular matrix in terms of variables here with the upper triangular matrix here. Now, what we are going to do is we're just going to correspond the elements of the coefficient matrix into the resulting matrix here. So, if we're going to write the coefficient matrix here, we have 1, 2, 1, 1, negative 1, negative 1, 1, 1, 1, 3, 2, 1, and then we have negative 1, 1, 2, and 1. So, for letter A, or if we're going to equate the first column with the first column here, we have A equals 1, B equals 2, D equals 1, and G equals 1. So if we're going to equate the first row here to the corresponding first row here, we have, right, so we'll have A times k, that's equal to negative 1. And since a is equal to 1, therefore k is equal to negative 1. A times L, that's equal to 1. And since a is also equal to 1, L would be equal to 1. A times M is equal to negative 1. A is equal to 1, right? So M would be equal to negative 1. For this row or this column or this part of the resultant matrix, since B, D, and G are already known, also K is already determined, we can solve for C, E, and H already, right? So we have B times K plus C, that's equal to negative 1. B is equal to 2, K is negative 1, and C, that is the unknown here, so this is equal to negative 1. Negative 2, transpose this on the right side, we have C is equal to 1. Because if we're going to transpose negative 2 on the right side, negative 1 plus 2 would be equal to positive 1. For dk plus E, that's equal to 1. D is equal to 1, K is equal to negative 1 plus E. So this is equal to 1. And since this is negative 1, if we're going to transpose it on the right side, we have 1 plus 1. So E would be equal to 2. Alright? So for GK plus H, that is equal to 1. Value of G is 1, value of K is negative 1, and then plus H, this is equal to 1. So basically H is equal to 2. Negative 1, if we're going to transpose negative 1 on the right side, we have 1 plus 1. So that's equal to 2. Now, for this one, we have B times L plus C times N. And that's equal to 3. Letter B is 2. L, alright, so L is solved to be or determined to be 1 plus C, that's equal to 1 times N equal to 3. So 2, that's equal to 2 times 1, that's equal to 2. Transpose it on the right side, so we have N equals 3 minus 2, or N equals 1. DL, alright, so DL plus EN plus F, this is equal to 2. So DL, that's equal to 1 multiplied by 1 plus EN, so E is 2, N is 1 plus F, and this is equal to 2. And if we're going to simplify this one, solving for the value of F, we now have 1 plus 2, so that's equal to 3, and then if we're going to transpose it on the right side, we have 2 minus negative 3, so that's negative 1. For this element, we have G times L plus H times N plus I, and that's equal to 1. So, G is 1, L is 1, plus H, our H here is 2, our N here is 1, plus I, that's equal to 1. So again, 1 plus 2, that's equal to negative 3, and then, 1 plus 2, that's equal to positive 3, and if we're going to transpose it on the right side, that would become negative 3, so 1 minus 3i would be equal to negative 2. Right, so we're down to our last column here. We have B, M, plus C times O. So this is now equal to Bm plus C times O, that's equal to 1. B is 2, M, right? So M is negative 1 plus C, our C here is 1, O is equal to, alright, so that's the unknown. This is equal to 1. So that's negative 2, or O is equal to negative 2 transpose on the other side, we have 3. So O is equal to 3. For this one, we have dm plus EO plus FP. So that's dm plus EO plus FP. This is equal to positive 2. dm, so D is equal to 1, M is equal to negative 1, plus E. Our E is equal to 2, O is equal to 3, F. F is equal to negative 1, and P, that's our unknown here. So this is equal to 2. So negative 1 plus 2 times 3, so that would be equal to 6. So negative 1 plus 6, that's equal to positive 5. And then if we're going to transpose it, that would be negative 5. So this is negative P equals 2 minus 5. So P is equal to 3. Because 2 minus 5 is negative 3. And then divide both sides by negative 1, that would become positive 3. And lastly, solving for J, we have GM plus HO plus IP plus J. That's equal to positive 1. So our G is 1, right? So 1, M is negative 1, plus H is 2, O is 3, plus I, our I here is equal to negative 2, plus P, and that's 3, plus J, that's equal to 1. So basically, 2 times 3, that's equal to 6. Negative 2 times 3, negative 6. So 6 minus 6, this will basically cancel out. And then 1 times negative 1, that's equal to negative 1. Transpose it on the right side. So J would be equal to 2. Alright? Now, we already solved for the values of A. Right? So we already solved for the values of A to letter P. Going back to our expression here, we now write the lower triangular matrix and upper triangular matrix with the corresponding values of A to P. So if we're going to write it here, L, or the lower triangular matrix, would be equal to, alright, so that's equal to A, B, C, D, E, F, G, H, I, J, and then this would be equal to 0. So A, that's equal to 1. B, that's equal to 1, or 2, I should say. Alright, so B is equal to 2. C is equal to 1. D is equal to 1. E is equal to 2. F is equal to negative 1. G is equal to 1. H. Alright, so H is equal to 2. I, that would be equal to negative 2. and j, that's equal to positive 2. So the upper triangular matrix of this matrix are all equal to 0. Now for the upper triangular matrix, this would now be 1, 1, 1, 1 because the diagonal matrix, the diagonal element of the upper triangular matrix are all equal to 1. The lower part would be equal to 0, and then this would, alright, so this would now be K, L, M, N, O, P. So K, we have, where is our K here? Oh, there it is. That's negative 1. L, we have 1. Right? So this is our L. M, that's negative 1. N, so that's positive 1. O, that's 3. And lastly, P, that's equal to 3. Right? So this is now the decomposition of the coefficient matrix into L times U. Now, we can proceed in determining the values of x1, x2, x3, and x4 respectively. But before we can do that, let us first solve the values of y. Since if we're going to use the LU decomposition, we're going to make use of the expression L times y be equal to b. So if our L here is this one, right? So if this is our L here, so we have 1, 2, 1, 1. We have 0, 1, 2, 2, 0, 0, negative 1, negative 2, 0, 0, 0, 2. Multiplied by y, we have y1, y2, y3, and y4. This would now be equal to the constant matrix, which is 1, right? So this is our constant matrix 1, 2, 3, and 3. So 1, 2, 3, and 3. So if we're going to multiply this matrix with this vector, we have this row multiplied by this vector, so we have y1, right? This row multiplied by this vector, so we have 2y1 plus y2. This row multiplied by this vector, we have 1, or that's equal to y1 plus 2y2 minus y3. And this row, or the sum of the sum of the products of this row and this column, we have y1 plus 2y2 minus 2y3 plus 2y4. And this is now equal to 1, 2, 3, 3. So the first unknown that we can solve here is y1 because that's equal to 1. So y1 is equal to 1. And solving for y2, so we have 2y1 plus y2, that's equal to 2. We're going to equate this one to its corresponding element here. So this is equal to 2 multiplied by 1 plus y2 equals 2, or basically y2 is equal to 0. Because this one, if we're going to transpose it, that is negative 2, and 2 minus 2 is equal to 0. So for y3, we have y1 plus 2y2 minus y3 equals 3. This is 1 plus 2 times 0 minus y3 equals 3. So negative y3 is equal to 3 minus 1, so that's equal to 2, or negative y3 is equal to 2, so y3 is equal to negative 2. And lastly, we have y4. So solving for y4, we have y1 plus 2y2 minus 2y3 plus 2y4 equals 3. So y1 is equal to 1, y2 is equal to 0, y3 is equal to negative 2, and y4 is the unknown one, equals 3. Right? So we have negative 2 times negative 2, so that's positive 4, plus 1, that's positive 5, and if we're going to transpose it on the right side, we have 2y4 equals 3 minus 5. So 2y4 equals negative 2. Divide it both sides by 2. We have y4 equals negative 1. So our vector y would be 1, 0, negative 2, negative 1. And we are going to use this vector y to solve for the values of x. Because the value of x, or we're going to use the expression u times x equal to y to solve for the values of x. Again, so writing the upper triangular matrix that we solved, we have 1, negative 1, 1, negative 1. So that's 1. Alright, let me just copy this one. So if I'm going to copy this, and then let's just put it in here. There we go. So this would now be x1, x2, x3, and x4 equals y, which is 1, 0, 2, negative 1. Right. So the value, or the unknown here that we can solve first would be the value of x4, because let us first multiply these two matrices. So in multiplying them, we have, right, so if we're going to multiply it, we have x1 minus x2 plus x3 minus x4. So multiplying this with this, right? So the second row with this column, we have x2 plus x3 plus 3x4. The third row with this column, we have x3 plus 3x4. And lastly, this one we have x4. And this is now equal to 1, 0, negative 2, negative 1. So x4 is equal to negative 1, because this one is, this element correspond to x4. For this one, right, so we have x3 plus 3x4, that's equal to negative 2. So x3 plus 3 multiplied by negative 1 equals negative 2. Or x3 equals negative 2 plus 3, because if we're going to transpose negative 3 on the other side, we have positive 3. Therefore, x3 is equal to 1. For x2, we can use this one, right? So we have x2 plus x3 plus 3x4 equal to 0. So x2 plus 1 plus 3 times negative 1 equal to 0. Therefore, x2 is now equal to 1 plus negative 3, so that's equal to negative 2. And then transpose it on the right side, we have positive 2. And lastly, solving for x1, we have x1 minus x2 plus x3 minus x4 equals 1. x1 minus x2, so that's equal to 2, plus x3, so that's equal to 1, and then minus x4, so that's equal to negative 1, equals 1. Alright, so solving for x, that should be x1. Solving for x1, we now have 1, or let me start here first, negative 2 plus 1, so that's negative 1, plus 1, so that's equal to 0. And this would now be equal to 1. Alright, so x1, x2, x3, and x4 are 1, 2, 1, and negative 1 respectively.